All right, so before I begin, I want to thank the organizers for the opportunity to speak. So I'm going to tell you about Nielsen realization and some of its consequences for infinite type surfaces. Everything that I'm going to tell you about is joint work with Santana Afton, Danny Caligari, and Joe Chen. So let me sort of give you an overview of the organization of my talk. So I'm going to tell you first 3 of our theorems. And then I'm going to sort of proceed one by one and talk a little bit more in depth about each of the theorems. So let's get started. So our results first. So our first theorem, this is the Nielsen realization, I guess, itself. Here's the setup. So let S be an orientable infinite type surface. So which types of surfaces are allowed? We're allowed to have boundary, but I'm going to insist that the boundary is a union of circles. So no infinite arc in our boundary. So the theorem says that finite subgroups of the mapping class group of S may be realized as isometries, groups of isometries of hyperbolic metrics on S. So a little bit about what kinds of hyperbolic metrics. So a finite type surface has finitely many isolated planar ends. Usually we call them punctures, right? If you want a hyperbolic metric of finite volume on your surface, then what you're insisting is that each of these isolated planar ends is really modeled on the pseudosphere and not on something like a flared annulus. So we're going to insist that our hyperbolic metrics will also have this property. So we'll have the nice sort of consequence of saying that any finite type subsurface of S will have finite volume in our hyperbolic metric. Great. So that's our first theorem. The other 2 theorems are really consequences of this first theorem. And they have to do with sort of the group theory of the mapping class group of S. So the first one says that topological groups containing torsion, so finite order elements, limiting to the identity, do not continuously embed in the mapping class group of S. So this provides some abstractions for various topological groups, some of which I'll talk about, embedding into the mapping class group of S. The other theorem that I'd like to tell you about also provides strong restrictions on the subgroup structure of the mapping class group of S. It says that compact subgroups of the mapping class group are finite and locally compact subgroups are discrete. There are lots of non-discrete locally compact subgroups out there, or groups out there, I guess abstractly, but none of them can be continuously embedded in the mapping class group of S. That's what this theorem says. Okay, so what I'm going to do is I'm going to first tell you about this first theorem here, and then I'll tell you about these 2. This first one goes by the name of Nielsen realization. Nielsen asked whether finite subgroups of the mapping class group of a finite type surface can be realized as groups of isometries. And Kirchhoff proved this in 1983. I think Kirchhoff's proof is really cute. So let me sketch it for you. So here's the setup. Let's give ourselves S, a finite type surface, and let's call T its Teichmüller space. And give yourself a finite subgroup of the mapping class group of S. Let's call it G. So the first step. Before I talk about that, what's the strategy? So the action of G on Teichmüller space, what we're looking for is a fixed point. Stabilizers of points in Teichmüller space are the group of isometries of that corresponding hyperbolic metric. So what this is saying is we are wanting a fixed point for the action of G on Teichmüller space. So that's what we're looking for. Okay, now let's continue. So we're going to consider a finite G invariant collection of simple closed curves, I'll call it gamma I, which fill the surface. So let me just remind you, that means that when you cut open the surface along all of these curves, what you get is a collection of disks, or one punctured disks. So the function from technicolor space to R that assigns to a hyperbolic metric. So S, I guess, equipped with a hyperbolic metric. So I'll call it X. So assigning to X the sum over I of the length of the geodesic representative of each gamma I is a proper function, and it's G invariant. It's G invariant basically because this collection is G invariant. And what proper means is that preimages of compact sets are compact. And then you can use the extreme value theorem to say that since this function is non-negative, it's going to achieve a minimum. So these functions that assign a length of a geodesic representative of a simple closed curve to a hyperbolic metric. These are real valued functions, and they vary convexly along these system of paths called earthquake paths. It's not super relevant what earthquake paths are. Basically, the idea is you're shearing the hyperbolic metric along a geodesic lamination. So you could think geodesic laminations are limits of simple closed curves. So take a simple closed curve and then do maybe some partial twisting around it. That would be an example of an earthquake path. And then maybe just sort of take limits of this. That's sort of the wishy-washy idea. And the functions vary strictly convexly. If the intersection of your curve with the lamination, so I'm writing nu for my lamination, if this intersection is non-zero, then the length function varies convexly along, strictly convexly along the path. So this implies that the function has a unique minimum. So let me like sort of sketch the idea of why. So let me sort of sketch the value of the function as height. So let's suppose we had two minima. So then we can connect these two minima by an earthquake path. There are enough earthquake paths to do this for any 2 points in technicolor space. All of our functions are varying convexly. So what that means is at worst, they're tracking the straight line between our 2 points, or like the graph is. So the convexity means that the graph lies underneath the straight line. That's what I'm saying. And at least one of our simple closed curves, since our surface, since they fill the surface, at least one of our simple closed curves is going to intersect the geodesic lamination along which this earthquake path is shearing. So actually, our sum, or our function, our sum of our functions, is going to vary strictly convexly. So it's going to have a graph that looks kind of like this. But this is a contradiction because we assumed that these 2 points were minima already. So that's why our function therefore has to have a unique minimum, which is fixed by G. So if you want to prove Nielsen realization for infinite type surfaces, maybe the first place to start is to say, okay, so what goes wrong just applying Kirchhoff's theorem directly? And what goes wrong is really this sum right here. In order to fill the surface, we need infinitely many simple closed curves. So we're adding up an infinite number of numbers, I guess. And there's no reason for this sum to converge. In fact, I think it should always diverge. So all the tools are there, but our series diverges. If you have thoughts about maybe how to weight these curves cleverly or something to get this sum to converge, please talk to me about it. I would love to prove Nielsen realization using Kirchhoff's proof. I think that would be really fun. Okay, so what do we do instead? So instead, we find a G invariant exhaustion of our surface by finite type subsurfaces. So let's call them like S0, S1, S2, and so on. And here's a picture, I guess. So I have Si minus 1 here in blue, and then adding the stuff in pink is what gets added when you go from SI minus 1 to SI. Oh, these subsurfaces are assumed to be connected. But the pieces, so I guess the complement of SI minus 1 in SI doesn't have to be connected. So it's called PI. And what we do is we apply Kirchhoff's theorem to each of these pieces, PI. So really the idea is you want to look at the stabilizer of the component, apply Kirchhoff's theorem using that stabilizer, and then sort of pull the metric back equivariantly in its orbit. And that will give you a realization of our finite group G as a group of isometries of this potentially disconnected subsurface PI. A nice fact about Kirchhoff's proof is that when you do this, you can insist that boundary curves have length 1. And what this allows us to do is this allows us to just glue back up all of the pieces together to get a realization of G as a group of isometries of a genuine hyperbolic metric on the whole surface. So that's the proof. Yeah, as I say, it would be really cool if there were a more analytic proof, but this combinatorial one gets the job done. So what I'd like to do with my remaining time is tell you about group theory. So let's go to our first theorem. That theorem was about torsion limiting to the identity. But before I tell you about the theorem, I just want to tell you about the topology of the mapping class group of S. So let's let C of S denote the set of isotopy classes of essential simple closed curves on our surface. So this is a countable set. It's a theorem of Hernandez, Valdez, and Morales that the action of the mapping class group of S on C of S is faithful. Given an action of a group on a set, you can always define a topology on the group in the following way. So it's called the permutation topology. And to define the topology on a group, you just need to specify what are your neighborhoods of the identity. And for us, they're going to be intersections over, finite subsets of C of S of stabilizers of points. So this is a general construction you can always do. You're looking at stabilizers of finite subsets of your set. So in our case, stabilizers of simple closed curves. It's a fact that this permutation topology, so there are a priori 2 topologies we could give the mapping class group of S. There's this permutation topology that I just described, and there's another topology that arises this way. So you give the homeomorphism group of your surface the compact open topology, and then give the mapping class group the quotient topology. And it's a fact that these 2 topologies agree. It's a theorem from the AIM workshop that the mapping class group of our surface embeds via this action here as a subgroup of the symmetric group unaccountable set. And this embedding realizes the mapping class group as a closed subgroup. Okay, so that's a little bit about the topology of the mapping class group of S. Let me tell you about torsion limiting to the identity. So a natural question to ask is, we have this embedding from the symmetric group unaccountable set into the mapping class group of S. Is there an embedding going the other way? And it turns out that no, at least not continuously. So let me tell you why. So first we have this proposition. So we're going to let gamma 1, gamma 2, and gamma 3 be essential simple closed curves in our surface, which co-bound a pair of pants. So here they are. The proposition says that the stabilizer, I guess the intersections of the pointwise stabilizers of these curves is torsion free. So let me just describe the proof to you in words. So if we had a finite order element in this set, then our theorem says that we can realize this finite order element as a group of isometry, or sorry, as an isometry of some hyperbolic metric on the surface. And what that says is that this isometry will fix the geodesic representatives of each of these simple closed curves, gamma 1, gamma 2, and gamma 3, and therefore it will descend to an isometry of the pair of pants that they co-bound. But the only isometry of a pair of pants that fixes the bounded curves setwise is the identity. So that's the proof. So this neighborhood of the identity in the mapping class group of S is torsion free. And that gives us the following corollary, that if you have a topological group containing sequences of finite order elements limiting to the identity, there is no continuous embedding of your group G into the mapping class group of S. Why? Well, because the torsion limiting to the identity has to go to torsion limiting to the identity in the mapping class group of S. But we found this neighborhood where the buck stops. There's no finite order elements cannot enter that neighborhood of the identity unless they're trivial. So what we've shown is that this map has to have some kernel if it's continuous. So the reason, I guess, that the symmetric group unaccountable set does not embed continuously into the mapping class group of S is because it has torsion limiting to the identity. Let me give you an example. So I'm going to write elements of the symmetric group unaccountable set in cycle notation. So here's an element. It swaps 1 and 2, swaps 3 and 4, swaps 5 and 6, and so on and so forth. So that's one element. It has order 2, so since disjoint cycles commute. Here's the next one. So it's going to fix 1 and 2, but swap 3 and 4, swap 5 and 6, and so on and so forth. And then the next one would maybe swap 5 and 6, so on and so forth. So this is a sequence of non-trivial elements of order 2 that limits to the identity in the symmetric group unaccountable set. Another interesting example of a topological group which contains torsion limiting to the identity is Q mod Z, which you could think of as a topological subgroup of, say, the circle group. Something that's why this is super interesting is this is a countable group. So a theorem of Algab, Patel, and Glamis says that you can actually find some surfaces S for which Q mod Z embeds into the mapping class group of S. And in fact, you can embed it as a group of isometries. But what our theorem says is that this embedding it's not continuous in the topology that I just described on Q mod Z. So there are embeddings of Q mod Z, but they have to be discontinuous, at least for this topology. So I think that's kind of cool. Yeah. And of course, there are lots of other groups that contain torsion limiting to 1. Another example of one would be the outer automorphism group of the fundamental group of the surface. So I guess this is maybe it's not surprising that that D. Nielsen bear should fail for infinite type surfaces, but this is one way of seeing it. Great. So let me tell you about our final theorem. So the final theorem says that compact subgroups of mapped and class groups are finite and locally compact subgroups are discrete. And what I'd like to do is I'd like to prove this theorem to you. So I'm going to start with a couple of facts. The first fact is that the mapping class group of S is Hausdorff and totally disconnected, basically because the symmetric group on the countable set has these properties. And it's a theorem of Van Danzig that totally disconnected, locally compact groups have a neighborhood basis of the identity given by compact open subgroups. And I just want to remind you, finite Hausdorff spaces are discrete. I think I gave this as an exercise in one of my in a topology class I taught. So it's a cute proof. So what this says is if we can show that compact subgroups are finite, then what we'll have shown is that our neighborhood basis of the identity is finite subgroups. And hence we have these open discrete neighborhoods of the identity. So this will show that if we can show that compact subgroups are finite, then we'll have shown that locally compact subgroups are discrete. Okay, so this reduces the problem to just showing that compact subgroups are finite. And let me tell you the strategy for doing so. So let's give ourselves a compact subgroup with a mapping class group of S. We'll call it G. And what we'll do is we'll show that G is torsion, so every element has finite order, and it's virtually torsion-free, so it has a torsion-free subgroup of finite index. Only the trivial subgroup of the torsion group is torsion-free. So what that says is the trivial subgroup has finite index in the whole group, so G is finite. This is my favorite way of showing that a group is finite. Great, so we have two things we want to show. And we'll be done. So the first one that we'll show is that G is virtually torsion-free. So we have our compact subgroup. It's a fact that compact Hausdorff totally disconnected groups, they're isomorphic as topological groups to profinite groups. And profinite groups have a neighborhood basis of the identity given by finite index open subgroups. So what that tells us is that if we have a neighborhood U of the mapping class group of S, a neighborhood of the identity, then its intersection with G will be an open neighborhood of the identity, and therefore it will contain a finite index subgroup of G. Right, I hope that was clear. But the proposition from before about those simple ghost curves bounding a pair of pans produced open neighborhoods of the identity that were torsion-free. So what that says is that G intersect such a U would contain a finite index torsion-free subgroup of G. So therefore, G is virtually torsion-free. Awesome. The slightly more complicated thing to show is that if G is compact, then all of its elements have finite order. So here we go. We're going to start with a simple closed curve. Its stabilizer is an open neighborhood of the identity. So G intersect the stabilizer contains a finite index subgroup of G. If you have a group G and a finite index subgroup, then given any element little g, there exists a positive power such that that power lives in your finite index subgroup. So in this setting, what that says is that every element of G acts periodically on every simple closed curve in our surface, every essential simple closed curve. So what we'll show is that if we have such an element, it has finite order. So the key tool here is the Alexander method for finite type surfaces. So let me remind you. So what that says is if we have a finite type subsurface, so here's my finite type subsurface, I'll draw it as a blob, and we fix our element of the mapping class group fixes every boundary curve. So here are my boundary curves, I guess. There exists a finite collection of simple closed curves in the subsurface such that any element of the mapping class group of the subsurface that fixes all of them has to be the identity. But so here's a finite collection of simple closed curves, and I know that I act periodically on all of them individually. So I can just take a huge common power, like maybe multiply all of the powers together, and I'll fix all of them. So what the Alexander method tells me is that G restrict or G to the n for some n, depending on the subsurface, so I'll write it as n of S prime, I guess, restricts to 1 on S prime for every finite type subsurface S prime of S. So we can use this to argue kind of as in the original proof of Nielsen realization. I didn't give the argument, but we can find an invariant finite type exhaustion. So an exhaustion of our surface S by G invariant finite type subsurfaces, such that the restriction of G to each mapping class group of each finite type subsurface has finite order. So to show that G itself has finite order, we just need to show that this order isn't blowing up as we sort of move along this exhaustion. And then the idea here is really the same as the proof of the proposition. So suppose S sub I contains a pair of pants. Then what we know is that any finite order element of the mapping class group of Si that fixes that the cuffs and the waist of that pair of pants is the identity in the mapping class group of Si. But this also holds for, so if we have Si is contained in Sj, and we look at the restriction of G to Sj, it has finite order. And so what we know is that as soon as it fixes that pair of pants back in Si, it actually has to be the identity on all of Sj. So what this says is that the power really that we needed to fix each finite type subsurface really cannot be blowing up. As soon as it fixes this pair of pants, it's the identity. So, so this tells us that G has finite order. So we've done it. We've shown that compact subgroups are torsion and they're virtually torsion free. So therefore they're finite. Great, so I will stop there. Thank you for your attention.